we've got this matrix. We're going to do the curl of each. I'm going to work through it. Okay, it's got X component, d, dy, h sub z. Looks like nothing. We don't have any y. Then here, minus z is 0. And then the next term, the 0 into the, finally something is d a sine omega t minus kx dx. Okay. So I'm looking at this one, and it's going to be along the y direction. And it has been, since you do the y1 backwards, you do doot doot, and then doot doot, we got a minus sign on it. Okay, and there's something that we can actually do math on. So here's an example that we can put through this thing and stop waving our hands around and get some numbers. And here it is. Okay, so we're going to get minus k, and we have that negative sign from doing the curl, a cosine omega t minus kx y hat. So really, we're just plotting through, kind of like what we did in chapter 1, using, or whenever we started to learn these differential operators, and we had something to work on, and it's no different. Okay, so we got this plus right here. That's the time derivative of the electric field. So finally we got rid of H. How are we going to turn magnetic field and amps per meter into electric field? Well, we're getting some extra constants. This is A is going to have units of magnetic field, amps per meter. This K has units of 1 over length. It's called the wave number. 1 over meters. It's not dark enough. 1 over meters. This thing, faradays per meter. And we have to integrate this thing once. So we're going to get our sign back. We're going to get E equals K. I can put a direction on it. A over omega epsilon. Omega is coming from integrating this thing once. And we're ignoring that there's some constant of integration that could come with this. We know there's not just a static standing electric field. Okay. And give me the rest of it. Sine omega t minus kx. I'm going to keep that y. So interestingly, we had a x-dependent magnetic field in the z direction. We got an x-dependent electric field in the y direction out of that. And it was just driven by this changing, spatially varying magnetic field, and gave us the time derivative. Okay. And so we can start plotting this stuff up. And there are plenty of good animations, not only of traveling waves in general. We can talk about traveling waves on strings and things, but of traveling electromagnetic waves. So they're showing you both parts. Let's see. So I took my usual coordinate system and flipped it around. So I have to be careful here to draw a right-handed system. But this is the x-axis. That's the one that everything's kind of wiggling on. And this is the z-axis. Did I do that right? Okay, and this was my magnetic field. Let's get a nice red marker out for that one. Okay, the original magnetic field, so h sub z. So I know I'm going to draw it along the z direction and have vary with x. Doot, doot, doot. A sinusoidal thing. Doot, 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 doot. Yeah. And this is a snapshot at a certain time, an instantaneous snapshot. Okay. And what do I have for the other side of it? When this one's at a max, well, this one's also at a max. It's the same thing. It's a sine. It's going to have different units. So it's a little bit of a weird plot. That this is the h-axis. This is the e-axis. And it's got units that are different because it's volts per meter instead of amps per meter. Okay. And Yeah, so we're following along. We have to think about, okay, we got plus x. If you want a right-handed coordinate system, your y-axis has to be plus back in this direction. Okay, x cross y equals z. So I have to draw my magnetic field, or my electric field, back this way. Okay, sine omega t minus kx up to some amplitude. It's got different units for each one. It's kind of tracking along. When it's negative, it's negative. Okay, and so you can imagine, and what I'll look for in this lecture series is a video of these things propagating along. This is just instantaneous. Instantaneous snapshot. Okay, in real life, it's not possible to get an instantaneous snapshot because we're thinking about things traveling at the speed of light. So a plane wave is getting launched, but it hasn't gotten somewhere yet, and there's a lag. So we'll have to build that in to our equations. But right now, we're looking at kind of a small section of this thing. Okay, where the amount of time it takes to for this thing to propagate. Okay, if you're thinking of it in terms of how long we need a snapshot to be for this thing to be instantaneous, it's a slow wave. Okay, so that's the plane wave example. If you want to practice, you can start making up other things that vary along different directions and see what you can do with them. Another thing that's interesting is to think about these plane waves in terms of their wavelength. Okay, we already talked about the speed, and how you find the speed is you say, well, where's this argument 0? It gives me something to look at when I'm looking at this wave, and later it's traveling along, it's moving. Okay, we can look at the speed, but we can also look at the wavelength. So speed, set this thing to 0, solve for x as a function of t. We did that. Omega, speed right here. The other thing is wavelength. We've got one period of this thing when this argument has increased by 2 pi. Then we come back around and it's the same again. Sinusoid is a modular thing. It just comes back around. So I'm going to move over on this side. Look at when this argument, omega t minus kx equals 2 pi. Okay, and we can think about how long does it take to do that. Okay, if we keep the time constant, now we're doing this snapshot thing at t equals 0. We're freezing this wave so we can look at it and measure it. Kx equals 2 pi when x is 2 pi over k. Okay, so that's your wavelength. We'll call out lambda.